A. Half a circle, fuller circle, right angle A. Now you say Coca-Cola. Okay. What I'm trying to say is, you can create the interest with all the students if you fall in love with mathematics. Interest National Seminar is a platform given to the students and research scholars to know what you're studying, to know the depth of what you're studying, and to show to you there are ways and means to achieve great ends. I wish this seminar, which is organized by the Department of Mathematics, leads you towards greater heights. You don't need to be a mathematician always, but remember, you are a student of mathematics wherever you go. We saw beautiful singing from our students. Usually, the students from the Department of Mathematics are very good singers. You know why? Because singing involves mathematics. If there is a keyboard, I'm not a mathematician, but I know a little bit. One note, or a note, if one note is missed, and that is mathematical note is missed, that is the end of the song. Okay? And if one note is down, the pitch will go down. Okay? All these you learn. If you want to be an A.R. Rahman, you have to know what mathematics is. If you want to be an engineer, you should know the length and breadth of what you are going to build. If you want to be a professor even, you should know the roll number of the students, and you should know the graph, row, column, everything. Only then you can be a very good professor. You should know, not necessarily you should know fuzzy theory, graph theory, fuzzy theory, what are the other things? Logic and so on. Logic is very essential for philosophy and other things. We have done logics too. Remember, there are a variety of things in mathematics. Most of us like us, we stop with arithmetics. But mathematics is still deeper. Deep down you have to go. This international seminar will give you one or two steps forward to know where you are and to know where you have to go and to achieve greater things in life. I wish you all the best. God bless you all. Thank you.
Thank you, Father, for your inspiring and delightful words. A well-educated mind will always have more questions and answers. Helen Keller. Now I invite Dr. A. Inswami, Deputy Principal of our college, a person who always initiated and promoted research, to felicitate the gathering.
Respected Reverend Father, God and Professor, Principal. Respected Dr. Purnaki, today's resource person. Respected Dr. Asir, our alumnus, and today's resource person. Dr. Alice Naran, controller and former actually of mathematics. Dr. Sundar, actually, Dr. Reverend Dr. Ravi, Vice Principal, and the Faculty of Mathematics, Dr. Vidya, the organizer of the program, and my dear professors and my dear students. Good morning to you and all. At the outset, I would like to share with you that our father principal, with all his humility, says he doesn't know mathematics, but being a musician, being a person who knows logic, you are full of mathematics, father, and that too only with profound understanding of mathematical ideas or mathematics theory. You can excel in your teaching in English, because there are in literature there are plays which could be handled with the persons having mathematics rigor. So in that way, I see our principal as a person who has mathematics with him, but with his humble heart, he says he is new to mathematics. So with that introduction, let me begin by sharing 17th century monument from mathematics to the world of humanity is the invention of calculus by Isaac Newton and Leibniz. and only from that onwards rocket science began. So that invention took us up to the information age. Of course, you would have heard about a famous physicist, Feynman, very famous physicist. He is also called quantum man. Nowadays, scientists talk about quantum computers. Of course, what we have up to now, it is called a classical computer or classical logic, zeros and ones. But when we come to quantum logic, you will have uncountably infinite number of states between 0 and 1, because the interval from 0 to 1 is uncountable mathematicians know. So quantum computers are being constructed by scientists and engineers from all over the world. 95% of work is over. And now I want to share with you another. So Feynman, he says, calculus is the language God talks. He says the universe is highly mathematical, and so he says God must be a mathematician. That's what famous physicist Feynman says. So that is the power of calculus, which has been to the progress of human civilization, and which is from the world of mathematics to the world of humanity. Coming to the 19th century, you have heard about the famous mathematician Galois. At least PG students, you are studying Galois theory. That is one of the papers. You have the title algebra, but Galois. Why I am bringing the mathematician Galois amidst you, because you have the topic for international conference graphs from algebraic structures. So for algebra, he gave a new life, new theory. Galois. He was born on October 25th in the year 1811. He lived only for 20 years. He lived only for 20 years. Before, the next day he was invited for a duel. D-U-E-L, duel. Kattichalla. When he was getting ready that night, he didn't sleep. He spent sleepless night. He wrote a 98 paper document. He didn't publish it, but later on his friend only published it, and that is called Galois theory, fundamental theorem of Galois theory. All PG students are studying that theorem. If you browse through internet, famous NPTEL lectures are there. You browse through Chennai IIT NPTEL lectures in ME engineering. There is a paper on Galois fields. So Galois, he has developed the association, the interplay between set of groups and set of fields, and he has created a group which is called by his name Galois field, right? That Galois field has got immense applications, and you should be aware that the mathematician Shannon developed the theory of information. He only coined the name bytes, okay, and he developed the theory of information, and he has used Galois theory there. And Galois theory, using Galois theory, Shannon has developed the information theory, and he is also instrumental. The mathematician Shannon is also instrumental for the development of artificial intelligence. The artificial intelligence is now booming, and we do not even guess, we are not able to guess where the humanity will be taken to using the field of artificial intelligence. That is the state. So in all these fields, we use Galois fields. And you know very well that it is used, Galois fields, Galois field, the area of Galois field is used in cryptography, and then people say it is even used in agriculture, and in electric circuit it is used. That's why in ME this paper is taught. So there is a world of applications for Galois theory. So you must you must learn more about Galois. Since you are learning fundamental theorem of Galois theory, you should learn more about the mathematician Galois. There are two theories, two stories about his death. First, one theory is that he was involved in politics and he was invited for a duel. He went for, he would have guessed that he could not win That's why the previous night he spent without sleep and writing 98-page document, and it was published later, and it has got that impact on humanity. So Galva's work has got a lot of impact on humanity, and today we have an international conference on graphs using algebraic structure. So when I heard about the title, I thought I could share something about the impact of Galva theory that second PhD mathematics students, second MSc mathematics students are learning, and so you should also get the spirit, the inspiration, and to contribute to the world of scientific community. And Galva would not have imagined that his theory would have dispensed impact for the purpose of humanity. So you should get inspiration. You should take inspiration from Dr. Purnaki and Dr. Asi, who are going to deliver talks today, and you come up with your own theory and you contribute to the world of scientific community, and your theory, if you are going to present your own theory, it may be useful in future for the progress of human beings. So I think you will make use of this international conference to the fullest. Wish you all the best.
Thank you, sir, for your words of information and felicitation. Now we move on to the first technical session. I take the privilege to introduce the speaker of the first session. It is with great honor and pleasure that I stand before you to introduce the scholar of exceptional caliber, Dr. Mohammad Reza Porraki, who will be leading the first session. Dr. Porraki is a name that resonates strongly within the international mathematics community, and for good reason. His contribution to mathematics, particularly in group theory, ring theory, and commutative algebra, have not only advanced our understanding of these fields, but also have inspired a new generation of mathematicians. Sir completed his master's degree from Sharif University of Technology, Iran, and postdoctoral degree from the University of Tehran. He did his postdoctoral research fellow from the Institute for Research in Fundamental Sciences. To add his feather in his cap, Sir has 3 ADAS number. Dr. Porraki received many academic honors from various institutions. Reviewer of the American Mathematical Reviews, member of the American Mathematical Society. Professor always stood first in his studies and received a number of academic awards. A few among them are Distinguished Professor Award for Research, TWKS UNESCO Associateship Award, in Mathematician Prize, and many more. Dr. Porraki visited almost 10 countries, including India, Germany, France, etc., and shared his knowledge to the students and the researchers wherever he goes. Sir gave 39 academic talks in various institutions. To his academic credit, Sir has published more than 80 papers in different journals. He wrote 7 textbooks in mathematics for universities and 2 textbooks in mathematics for school students. Professor presented 6 invited expository papers in Persian. Sir supervised 29 MSc projects. Under his able guidance, 2 members completed their PhD. Since time is not enough to say all the achievements of our exemplary scholar, please join me in welcoming Dr. Mohammad Reza Porraki to the stage. Sir, the floor is yours.
கலெக்ட் பண்ணி இந்த பக்கம் கனெக்ட் பண்ணிக்கலாம். இது வேணும் இதுதானே ஓபிஎஸ்ல பண்ணு இல்லை வீடியோ உண்டு ஜி அது எக்ஸ்டெண்ட் பண்ணால் வர மாட்டேங்குதையா? எது அது டூப்ளிகேட் இல்லை, அதுக்கு இல்லை, கேமரா வேறு கேமரா. ஆமாம், நீங்கள் வேறு வயர் இல்லையா நம்மள்கிட்ட? ஆ இல்லைப்பா, அந்த ரெண்டையும் கனெக்ட் பண்ணுறதுக்கு வேறு வயர் இல்லையா? அது என்ன டிரைவரா? ஆமாம், ஆமாம். சரி, இப்போ என்ன செய்யலாம்? என்ன செய்ய வாங்கிட்டு வரல? சரி, டிஜிட்டல் கேமராவா? அது வேணும், டிஜிட்டல் பண்ணலாம். ஆமாம், சொல்லு. இல்லையா? ஆ அந்த பாடம் வைக்கணும். நடுவில் வைக்கிறது அடுத்த இருக்குங்களா?
அதுக்கு மைண்ட் இது வேலை செய்யலை அப்படின்னு கன்ஃபார்ம்
இது வேலை செய்யலாம்.
சரி, இந்த ஒரு நாலு பின்ன இருக்குங்க, அது கொஞ்சம் ரெண்டாக இருக்கும்.
சரி சரி.
Thank you very much for coming, and thank you for the organizers for inviting me. I want to talk about some topics about brains and cracks and some relation between these two things. So I think that the students can follow easily. You know what the notion of brain, yeah? I think all of them brain or no? Yes, you know the notion of brain, and also you are familiar with graph. So I will talk about this. But first of all, for informal part of my talk, I want to fix two notation, and I say something about the history of the problem, and then we go to talk about the problem, okay? Then are the array. So we have a ring. You know that what the unit element is. Unit element is an element of R that there exists a peak in R such that U be equal to U equal 1. This is the unit element, definition of unit element. And in this talk, when I talked about ring, I mean that it is a ring with unit. And we assume that the unit of ring is not equal to 0 of ring, because we want to have a new trivial ring. Because when 1 is equal to 0, then ring is 0. So always we assume that R has unit. and this is the unity of R. So this is the meaning of unit element. And I want to use another notion that is R is generated by its units. Then we say that R is generated by its unit. We say that R is generated by its units. In fact, this is definition. We know that all definitions are written only. If there exists U1 to UK in R, that are units suppose that x also is given, then for all of x, right here, for all of x in R, there exists U1 to UK in R such that we can write x in this. If this happens, we say that R is generated by its units. But in literature, they say that R is generated additively by its units because we use addition here. So, my talk today is about generally this. So, again, we say R is generated by its units if and only every element in R can be written as the sum of unit elements of. Okay? So, I want to say some history of the problem. In 1953 and 1954, two persons, Wilson and Zelensky, this year was starting point for study of this kind of problems. See the results of these two persons. Imagine that D is a division ring. Division ring is a ring with unity, and every non-zero element has inverse. It is as same as fields, but in fields we assume that the multiplication is commutative, but here we remove the commutative. Okay, so assume that he is a division, it would be a field also. But assume that it is not Z2, except C, and let V be a finite dimensional vector space over D. Probably you have studied linear algebra and you are familiar with vector spaces, but we study generally vector spaces about fields, but the ground, the domain here is a division instead of field. The study of vector spaces over division rings is also same as the study of these spaces over a field. And here I assume that diamond B is not equal to 4. So we have to assume or division range is not Z2 and or the vector space has dimension not equal to 1. Then they prove that every T, what is T? Linear transformation. Every T, linear transformation, can be written as a sum of two non-singular transform. You know that linear transformation. The linear transformation, a linear transformation is a function as t from b to b, that t of x plus y is t of x plus t of y, and t of, for example, cx is equal to c t of x. So it's linear transformation. And non-singular transformation means one-to-one and onto linear transformation. And they prove that in this case, every t linear transformation on V can be written as a sum of two non-singular linear. What is the translation of this result in the language of rings? If you gather together all linear transformation over V here, and you call it the set of endomorphisms of V over D, okay? Then endomorphisms of V over D with usual sum of functions and composition is a ring. And so linear transformations are elements of this ring. And you know that non-singular transformations are in fact unit elements, because when you have a non-singular transformation, it is one-to-one and onto, and so it is invertible with respect to composition. And so for every t you can find a linear transformation in this format, that composition is identical. So here non-singular transformations in this ring means unit elements. Therefore, in fact, these two mathematicians in these years proved that every element of this ring can be written as a sum of two units. Here, K is 2. So, I can say that if D is not equal to C2 and diamond B is not equal to 1, then this ring is generated by its units. Every element in this ring can be written as a sum of two units. So it was the starting point for a study of this problem. After that, in 1958, Korniakov, another mathematician from Russia, posed a question: which regular rings are generated by their units? Because the problem in general is very hard to solved. But he posed this problem. Irregular rings, in fact, can be generated by its units. And also, he posed a special question. This question was this: is every element of a von Neumann regular ring? This question was about regular ring, but he added the assumption of von Neumann regular ring. Is every element of a von Neumann regular ring, which cannot Z2 as a quotient, I will tell what the meaning of this, can be written as a sum of units. So he asked a question about this, but he assumed that R or ring is von Neumann regular and does not have Z2 as a quotient. I will talk about this. This was a question in 1958, but after that, some years ago, in 1977, Bergman was answered negatively to that question by constructing a von Neumann regular that which has not Z2 as a quotient, but it cannot be generated by its units. So the problem of or the question of Spermicro was wrong. In 1968, Ehrlich, an area of workout discard and produced a systematic study of rings generated by its units, and in fact constructed a large class of this kind of rings. In fact, its theorem is this one, this statement. Assume that R is a ring, so we have a ring. 2 means 1 plus 1 in rings. 2 is a unit element, and for every A in R, there exists U in R such that A U A is equal to A, and this is unit. This is the meaning of von Neumann regularity. And we proved that if this happens, then every element of R can be written as sum of 2 units. So in this large class of regular von Neumann rings, he showed that this is true, and this kind of rings generated by students. After then, in 1974, Raphael studied again the rings generated by its units and found another class of this kind of rings name S rings. In that way, they call them S rings. And in 1976, Fisher and Snyder proved this theorem. Imagine that R is a von Neumann regular ring with primitive factor rings Arcadia. We don't need what it is because we don't work with this today. So R is a von Neumann regular ring with primitive factor rings Arcadia, and also suppose that 2 is a unit. Then they prove that this kind of rings can be generated by their units. So you see that in literature, starting from 1953, we have many results about rings which are generated by their units. So it's very important problem. And the basic problem, starting point is this. And I think this one is most important because have many applications in linear algebra. That in this case, every transformation can be written as a sum of 2 unit elements of this ring. So the problem has a very rich history. And today I want to talk about a theorem by Raphael that published after this one. Let me write the statement of the theorem and then we talk about this. If you have any question on it, please ask. No question? So the important thing that you should see that is that this theorem has a rich history and it is important. Let me write the theorem that today I want to talk about. Let R be a finite so here in this theorem R rings are finite. Let R be a finite primitive ring with 1 not equal to 0. Then R is generated by its units if and only if R cannot have C2 times C2 as a quotient. This is a theorem of Raphael. Published in Journal of Algebra. One of the famous journals of algebra, journals algebra. And I think in 1973 or 4. I don't know exactly. This is the theorem. And the paper has, I think, about 12 pages, including many advanced results, and at the end, they arrive to this theorem as a corollary, using previous lemmas and propositions that proved in the paper. Okay. Today, I want to give a proof for this theorem using graph. Very, very easy proof that you can follow. You cannot read the proof of Raphael in Journal of Algebra because it needs many other knowledge of algebra, advanced knowledge of algebra, but at this talk I want to give a proof by graph theory for this theorem. So, because of our main purpose of this talk, one more time review the terms, and then it's algebra. R be a finite commutatively. Finite means that the number of elements of ring is finite. Commutative ring, you know that, and 1 is not equal to. R is generated by its units. I explained. If and only R cannot have Z2 times Z2 as a quotient. What is the meaning of? The meaning of this is there no exist ideal of R such that R over I is a quotient ring. This is isomorphic to Z2 times Z2. So when, for example, when I say that R has Z2 as a quotient, it means that there exists an ideal that R over I, that ideal is not. R over I is isomorphic to Z2. Here, R does not have Z2 times Z2 as a quotient, means that there is no ideal I of R, that R over I is isomorphic to Z2 times Z2. Okay. For proving this theorem, I should explain some notions. The first one is that I want to assign a graph to a ring. Okay? This is a ring. I want to assign a graph. I should explain some notions. The first one I denote by one. Okay? This is graph. Okay, what is the definition of this graph? V of R means the vertex set of this graph is R. So the vertices are the elements of R. And since R is a finite field, we have finite number of vertices. what is the edges in this graph? Because for defining a graph, we should show the vertices and show that the edges are equal. Okay. X and Y are distinct. These node to this point, they are distinct because after a while I want to remove this word, but for now, as usual, when we define a graph, we want to define a single graph. So we have two distinct vertices, and we say that they are adjacent if and only if x plus y is a unit. This is the set of unit elements. The set of unit elements of. So you can easily draw the graph for easy rings. For example, consider R is Z3. Z3 has 0, 1, 2 as elements, and you know that either sum and multiplications are 1, 2, 3. Okay. What is the vertices of this graph? 0, 1, 2. Okay. 1 plus 0 is 1. 1 is unit here. So we have this A. 2 plus 0 is 2. 2 is unit here. Y is unit because unit element. Y 2 plus 0 equal 2 is unit because what is it? It's inverse. It's center. 2 times 2 is 4. 4 is 1. And we don't have any edge here because 1 plus 2 is 3. 3 is 0 and 0 is the non-unit. So this is the P of R when R is 0. Okay. Now, so we have a graph which we construct it using bar or ring. Okay, imagine that R can be generated by its units, okay? I want to check something. Assume that A is an arbitrary element of R, okay? Since R can be generated by its unit, we can write A as U1 plus U2 into K, where these are unit elements. Yes, this is the definition. Now, is 0 adjacent to U1? Because the sum is U1, U1 is 2. Is U1 is adjacent to minus U1 minus U2? The sum is minus U2 is the unit. this element is adjacent to this, again yes, and so we can go to this element, u1 plus uk, that is equal to a. But then we arrive to u1 plus u2 plus uk. Because you see, when k is even, it ended here, minus minus. For k odd, we have plus plus, and again for k even, we have minus u1, minus u2, minus u3, minus u1, which is again, we have a. So this happens when k is odd. Yes. But if k also even, we can arrive to a. In which way? 0 is adjacent to minus u1. Yes? Minus u1 is adjacent to u1 plus u2. u1 plus u2 is adjacent to minus u1, minus u2, minus u3. And then when you arrive, or in fact you can arrive to this if we assume k is e. You accept or not? If k is odd, you can make this work, and if k is even, you can make the other one. Why I say walk and I don't say path? Because in path we don't have repeated vertices. But maybe here we have repeated vertices. So I say walk. So what is the result? Anyway, we have a walk between 0 and a, which a is an arbitrary. So between 0 and any vertices, we have a walk. So imagine that you have two vertices, x and y. You have a walk here from 0 to x, and you have another walk from, for example, 0 to y, and joining these two walks together, you have a walk between x and y. X and y are arbitrary. Yes? But if you have a block between x and y, you can make a path. Because imagine this is a block with repeated vertices, but you can make this path. It is a very easy exercise in graph theory. And if you have a block between two vertices, then you can reduce it to a path. So, what is the result? If R can be generated by its units, this graph is connected because every two vertices can be joined by a path. it is natural to ask whether the inverse is correct or not. Not. If G of R is connected, can we say that this happens? Yes. In fact, the answer is positive. Imagine that G of R is connected, okay? Suppose that V is the sum of some units. Sum of some units. Imagine that V is sum of some units. And imagine that V is adjacent to A. Okay? Then easily you can say that A also is sum of some units. Why? Because when we have A and H here, then A plus B is a unit by definition. Okay, what is the meaning of A plus B is, for example, U. U is unit. B also is sum of some units. The negative of units also are units. So A is sum of again some units. So if B is sum of some units and you have an A from B to A, automatically A also is sum of some units. Okay. See, when G of R is connected, for all x in R, you have a path between x and 1. Definition of connectedness. Every two vertices can be joined by a path. For all x, you can connect from x to 1 by a path. 1 is sum of some units. Here, in fact, sum of 1. So, this is sum of some units, this is sum of some units, this is sum of some units. So, x is sum of some units. But x was really arbitrary, so every x is sum of some units. It means that R can be generated by its units. Correct? No problem. So, see, our theorem is that R is generated by its units if is happy. No, we have R can be generated by its units if G of R is connected. No, the main question is that can we prove that R cannot have C2 times C2 as a quotient? Is equal. If you can prove that these two are equivalent, then in fact these two. Correct? Okay. So we switch to this part and see what can say about this. Correct? So we switch to this part and see what can say about I want to define another. I define this graph. The elements of R are vertices, and these things X and Y are joined if and only if X plus Y is a unit. If we remove the word business, then we have this graph. So this graph has loop because I removed the word business. Okay? So for example, if again I consider this, then if I want to draw this graph, the vertices are again this. Of course, we have this one. And also we check extra ones. For example, 0 and 0 are adjacent or not. 0 plus 0 is 0. Is not 0. 1 plus 1, 2. 2 is unit. So we have a loop here. 2 plus 2, 4 is equal to 1. So we have another loop. So this is GR1. The graph may have loops. Okay? No. If 2 is not unit of R, then these two graphs are equal. Why? Because imagine that you draw the first one and you want to check that X in vertex X you have a loop or not. X plus X equals to 2X. If we have a loop, 2X should be unit. It means that 2X, for example, U should be equal 1. But in that case, when we have 2XU equal to 1, 2 itself is unit. Comes to that. When 2 is not a unit, X plus X is never equal to a unit. So we don't have a loop. So these two graphs are equal. But what is the importance of this new graph? You know the definition of Cartesian product of two graphs. You have two graphs. There are many products between graphs. One of them is Cartesian products and has different notation for showing that. What notation is that? I use this. G1 is a graph, G2 is a graph, and I want to say what this graph is. The vertices are this graph are x1, x2, where x1 vertex of G1 and this is vertex of G. In fact, the vertices of this graph is Cartesian product of G1 and G. And then we say that two vertices are adjacent. We say that x1, x2 is adjacent to y1, y2. Note that these two vertices are this way. Then we say that they are adjacent. Then x1 is adjacent to y1 in graph G1, and x2 is adjacent to y2 in graph G. This is the definition of Cartesian curve. Note that when these two vertices are distinct in this graph, maybe x1 and y1 are equal. Because, for example, 0, 1 and 0, 2 are two distinct vertices, but 0, 0 in graph. And the point of this definition is that if we are a ring R and if we are a ring S, then we can talk about G of R times S. This is the product of two rings, correct? This is product of two rings. And I want to study it is isomorphic with graph. In fact, it is isomorphic with this one. You can easily check that as easy exercise. By this point, see, consider two vertices here. One of them x1, x2, one of them y1, y2. x1 and y1 come from R, and the other one comes from S. And these are distinct. And you have an edge between this. So you make an edge in this graph. But when you move to these graphs, you see that what is the meaning of that? This is adjacent to this. x1 and y1 should be adjacent in G of R, but maybe x1 and y1 are equal. So in fact they are adjacent in J R bar, not in J. In G R bar, not G R. Because maybe they are equal also for this one. x2 and y2 are adjacent, but maybe they are equal, so they are adjacent in this graph. So the point of Cartesian product and the point of this graph is this important vector. No, I want remember this, and no, I want to attack this problem. R is a finite quantity ring. There is a basic theorem. It is difficult theorem, but it's very important and basic. I mean by basic that we use it in many theorems and demos. And that theorem says that every finite quantity ring can be written as product of finite local rings. What is the local ring? Local ring is a commutative ring that has only one maximal idea. For example, if you denote the maximal ideal for R1 or for Ri with Mi, you use this notation. You say that Ri and Mi is local, and this Mi is the maximal ideal of R. So it is very, very important theorem that says that every ring can be written as a product of locals. Okay? When you write R as this format, then you arrive to this one. It is trivial when two rings are isomorphic, the graphs associated them also are. But what can we write about this one, this part? In fact, if k is equal to 2, then it is yes, and if k is greater than or 3, you can use induction to write this. Correct? So for every finite complete ring, we can write these things. You can write R in this format, and G of R in this format, and in this format. For all rings, okay? No, imagine that R cannot have Z2. Imagine that R has Z2 times Z2 as a quotient. It is here. Imagine that R has Z2 times Z2 as a quotient. I want to write here something. So imagine that R has Z2 times Z2 as a quotient. Again, you can easily prove that if R has Z2 times Z2 as a quotient, then you have 2 or more local rings that Ri over Mi has size equal to. You can prove it. It's easy as an exercise in abstract algebra, basic abstract. When R has Z2 times Z2 as a quotient, it means that 2 of them has quotient ring with size 2. Maybe more than 2 they have this property, but at least 2 of them has this property, because we say that has Z2 times Z2 as a quotient, okay? Maybe the other Z2 also there are, but has Z2 times Z2 as a quotient. So 2 of them has this property. And with reordering, we can assume that I equal to 1 and 2 has this property. That R1 to M1 is equal to, and R2, M2 is equal to. So if we assume that R can have Z2 as Z times Z2 as a quotient, then we have a composition in this format that we have R1 over M1, R2 over M2 has size. No, I want double composition. Let R, M, be a local ring. Then 1. It has two parts. I write first one. If R over N is equal to, then G of R is a complete bipartite graph. I will prove, but I want first music and then. So when R over a over its maximal ideal has size 2, then I want to prove that G of R is complete bipartite. Okay? Let me prove it and then easy to check. See, what is the meaning of R over N has size 2? It means that this is R, this is N, and this is R minus. In fact, as an additive group, R has two cosets. One coset is M, and the other coset is R minus M, that we can write it as A plus M, where A is not in M. You know from basic algebra. One coset is 0 plus M or M, other coset is A plus M, A is not. Okay? I want to prove that G of R is a complete bipartite graph. I want to say that the partite sets are these sets. These are the partite sets. You can put vertices here, this is N, this is A plus N. And by this division, you can make the graph. You can in fact see the graph as a complete bipartite graph. For complete bipartite graph, we can check that we should check that there are no edge between them. Okay. Say X, say Y. Is there an edge here? If you say that there is an edge here, so X plus Y is a unit. Okay? X is in M, Y is in M, X plus Y is in M, so you find in M an element which is unit, but it cannot happen. Because when a unit element is here, then M should be R and maximal ideal. So we don't have any X. What about this? Here also we don't have any. Because imagine that X is here, Y is here, and you write, and you have an H here, okay? So X plus Y is a unit, correct? X is element of here, you can write it A plus M1. M1 is an element of here. And you can write Y as, note that this coset is equal to A plus M, also equal to minus A plus M. Because minus A also is not. So you can write Y as minus A plus M2, where M2 again is M. This is unit. So M1 plus M2 again is a member of M, which is unit complex. So you don't have any H here. And every vertices from the all partite set is adjacent to other one, because choose x here, y here. Okay? Imagine that x plus y is not a unit. I want to show that there is an h. Imagine that there is no h. So x plus y is not in U of r. X plus y is not U of r. It is an easy exercise in algebra that in local rings, the set of invertible elements are here. And non-unit elements exactly the same. So when this is non-unit, it means that it is in M. X also is in M. So y should be in M. But y is not in M. Okay? So you have a complete bipartite graph. This is the proof of that proposition. C, I assume that R has Z2 times Z2 as a quotient. So when write R in this format, I found that two of them has this property. That 2-1 I consider that is the pairs 2-1. So R1 to M1 and R2 to M2 have size 2. And then I wrote this, okay? But note that when R1 to M1 is equal to, or this happens, then 2 is not a unit. Because where is the one? In the above part or 1 in the above part? Another one is 1. Both of them in the above. So there is no h between them. 1 plus 1 is 2. So 2 is not unit. Because if it is unit, then so 2 is not unit. When 2 is not unit, I can remove this. I can remove this. Because for I equal to 1 and I equal to 2, I have this, I have this. So this graph in fact has no loop. This graph has no loop. This is also same. This is also same. So we arrive to this one. Note that it is an easy exercise in graph theory that Cartesian product of two bipartite graphs, there is no need to compute here. The Cartesian product of two bipartite graphs is this kind. Since we have this one and this one, so this is by that proposition. This is bipartite, this is bipartite, this is bipartite. So the result is disconnected. The result is disconnected. So all is disconnected. So what is the result? We assume that R has Z2 as a quotient. We arrive to G of R is disconnected. So if G of R is connected, then R cannot have Z. So this is the proof of this part. We assume that G of R is connected. We want to prove this. If in contrary, suppose that this not happen, then we arrive to so this part. What remains is to prove that is. If I can prove that part, then in fact we have a simple proof comparing with original proof of this theory. We have a simple proof using graph theory for this part theorem, integral theorem. So now I want to prove this part. R cannot have Z2 times Z2 as a quotient. I want to prove this. G of R is finite. Again, I write R in this format. And the maximal ideal of Ri is M. Again, I write in this format. So I have this one. So, this. What happens when we assume this? R cannot have Z2 times Z2 as a quotient. It means that when we divide Ri's to Mi's, two cases can be active. None of them is equal to 2. It means that we have not Z2. Or one of them just equal to 2. That means that just we have one Z2. Because we say that R cannot have Z2 times Z2. It means that we don't have 2 Z2 in that quotient ring. So, two cases can be appear. One, Ri over Mi is greater than 2 for all I. It means that in this ring we don't have any Z2 as a quotient given Z2. Or R, for example, Ri over Mi is greater than 2 except one of them. That one we can say R1. So we have R1 over M1 is equal to 2, but Ri over Mi is greater than 2 for all I between 2. These two cases we have. Okay? Now I want to write another proposition. The part 2 of that proposition says that part 2 says that R over M is greater than 2, then for all X and Y in R, this is the set of neighbors of X. Neighbors of X is the vertices that join to X. If the graph is simple, it is clear. But if the graph is not simple and has a loop in X, we add X to this by definition. So in graphs with loops, it is exactly the set of neighbors plus loop. I can also easily prove this. See, this is M. In fact, the non-units and other one are unit elements. Okay. So when, for example, R over M has size 3, exactly 3, then the size of UR is equal to 2 over 3 of R. 3 parts, 2 parts are units, exactly. But when R over M is greater than 2 size, then we have more units comparing this. So this is u of r is greater than or equal to 2 over 3 size of r. No, it is easy to see that for all x in R, you have this. It is easy to check that. Why? Suppose x is an arbitrary element. Okay, there is two cases. 2x is not unit or 2x is unit. First, assume that 2x is not unit. What is the meaning of 2x is not unit? Means that in x we don't have any loop. Okay. So when we don't have any loop here, look at u minus x when u is in u of r. U minus x is distinct to x because if they are equal, then u is equal to 2x and it means that 2x is distinct. So they are distinct and they are adjacent. Why adjacent? Because the sum of them are u unit. So all of u minus x at u in R is a neighbor of x. And we don't have any loop, so there is no problem. For this case, 2x is an element of u of R. Then see x and consider u minus x where u is in u of R minus 2x. See, in this case, 2x is unit. I remove the unit, okay, u of R minus 2x. So for all u in this set, again, this is distinct to this, and we have an edge between these. So u minus x for u in u of R minus 2x, we have, this is subset of this. We should add to this set also 2x because 2x minus x is x. That means that these two are equal and we have a loop here. So we should have 2x here. So we have a set that we remove 2x here and again add 2x there. So this is the same. So we have this. And this shows that this has this number. Because there is one-to-one correspondence between these, and so this is less than this. And we can finalize why this, see? So this intersection has exactly this elements, this number of elements. This is using this, using what? Using this is greater than or equal this. Minus R. And u of R is greater than this. So 2 over 3, 2 over 3, 4 over 3 R minus R. Is this and this is positive. Since it is positive, so it is not. The time is over, yo. Yeah. What? 5 minutes? Oh. In 5 minutes I did. So we have this proposition 2 and see how we can use this to prove this. I just complete this one. This one also same as the first one. Imagine that Ri over Mi is greater than 2 for all I. Okay? So, for all I, N G bar Ri X intersection N G bar Ri Y is null. Okay? Now, assume that instead of the study of this graph, we study this graph because they are isomorphic. Consider two distinct vertices, x1 to xk, and y1 to yk. Two distinct vertices. For this comes from R1, this comes from R2, and so since Ri over Mi has size greater than 2, so for all I, this intersection is null for all I. So you can choose a Zi from this. So Zi is the neighbor of Xi and is the neighbor of Yi. So you can write this. To see that you can construct a plot between x and y. Here, distance of x and y is less than or equal to, so diameter of the graph is less than or equal to. In this case, again we use this kind of words, it is easy. And we found that in that place, diameter of graph is less than or equal 3. So note that we prove this part. We assume that R cannot have Z2 times Z2 as a quotient, and between every two vertices we made a walk or path. So this conclusional implication also is correct, and I prove a more thing. See, here diameter is less than or equal 2, in the other part diameter is less than or equal 3, and so we can say that when R cannot have Z2 as Z2 times Z2 as a quotient, then we can write every element of R as a sum of at most 3 units. Not only this is correct, R cannot have Z2 times Z2 as a quotient, then R is generated by its unit. This means that every element can be written as a sum of units. If we prove that, we can write every element as a sum of at most 3 units. And this is also the other corollary in this case. That after that says that in fact all proof shows that we can write it as product at most 3. And now you see that how graph theory can use for proof of a very difficult theorem that was published in journal. This is a paper of mine. I said is published 10 years ago in Elemente Dermat. After that, we call this graph as unit graph, and in fact, the unit graphs was born. And after that, many papers about unit graphs were published by many others. But it was the starting point of definition of unit graph.
Is there any questions from the audience? Is there any questions from the audience?
There are any questions in the price?
If no question, once again clapping your hands. Thank you for your presentation, sir. You have introduced as a new theoretic graph for researchers. I think many researchers will use this in the future work. Now, I request Dr. S. Sujit sir to present the token of love for a resource person, Dr. M. R. Koti. It's time for the break. So tea and snacks are arranged for everyone at the back side of the building. So please have the tea. And then after the tea, the paper presentations will start. So paper presenters who have the PPTs, please submit your PPTs to the front desk. And the paper presentation will start exactly at 12 o'clock. 12:30. So please have your tea break and come again here at 12:30. Please be here at 12:20. 15 minutes break. Please be here at 12:20. The paper presenters, please give your PPTs at the front desk. Ms. Ponchila, Sublakshmi, Sugita, Admin Chaya,